Hello APC Mechanics students in Unit 1 Kinematics, Class 3, Motion in One Dimension, Part 3. Then previously, if you remember, all the variables of motion that we introduced depends on the type of motion. So before we do anything, we used to specify the type of motion. However, some quantities can be introduced without referring to the type of motion, like the average speed and the average velocity. We can define the average velocity and the average speed along the x direction. For example, the average velocity is given by displacement over delta t, and delta x would be the displacement, which is the final position minus the initial position, and delta t would be t final minus t initial, known as the duration. The average speed, however, would be distance over delta t, and we know what's the difference between the d and delta x. Now, average velocity is a vector quantity, while the average speed is a scalar one, and all SI quantities hold true, and similar definitions can be generalized in the y direction. Now, example 1, a particle P moves along a directed straight line. At t1 is 3 seconds, the particle is at a point of position x1 8 meters. At a time t2 8 seconds, the particle is at position x2 is negative 2 meters, and at a time t3 12 seconds, the particle is at a position x3 is 2 meters. We need to find the average speed, average velocity, and we need to explain why A and B would not be the same. Now here, they didn't specify anything about the type of motion. For this reason, we are able, independent of the type of motion, to calculate average speed and the average velocity. Then the best way to tackle such type of problems is to represent the oriented axis and to place the different positions. Now, initially we started with 1, went to 2, then back to 3, and if you want to calculate the average speed, we need to find the distance going from 1 to position 2, that would be 8 plus 2, which is 10 meters, going from x2 to x3, that would be an additional 4 meters, then the distance is 14 meters. The duration delta t, the initial instant is 3 and the final instant is 12, then 12 minus 3, that would be 9 seconds, and the average speed would be given by 14 over 9, which is 1.56 meters per second. Now for the average velocity is displacement over delta t. The initial position is x1 and the final position is x3, independent of x2. Now x3 minus x1 would be minus 6, and the duration remains unchanged, and by that the average velocity would be delta x over delta t, which is minus 0.67 meters per second. And as we can notice that both answers are in the same. Why they are in the same? Simply because v average is a vector while s is a scalar, and generally they are not equal. They are equal if the motion is along a non-changing direction. So if we don't change direction, and by that the displacement and the distance would be the same. Whenever we change direction, there is a turning point, the displacement would be different than the distance. Now, average velocity, constant acceleration. So notice that here I'm introducing the average velocity. We know that the average velocity in this case is given by delta x over delta t, but now I'm gonna introduce a new formula that is specifically related only for the constant acceleration. In the case of constant acceleration, we can provide an alternative definition for average velocity, and this is given by the final velocity plus the initial velocity divided by time. All SI quantities hold true, and similar definitions can be generalized in the y direction. This relation can be used if and only if the acceleration is constant. And remember that this is the table in which the acceleration is constant or 0, and now we can add it to the last row, and by that we have completed the table of the constant acceleration. Now what about, so let me recap. We have talked about the average velocity, average speed, average velocity in the case of constant acceleration. Now we can talk about the average acceleration. This is also independent of the type of motion, and it's given by the variation in the velocity delta v over delta t. Then delta v would be v final minus v initial, and delta t would be t final minus t initial, and all SI quantities hold true, and we can generalize this definition in the y direction. In example 2, we have a vt graph For an object moving in a straight line, what is the average acceleration of the object during the first 8 seconds? Then that would be the initial instant, and that would be the final instant at 8 seconds. So let me erase the inking. Now average acceleration is delta v over delta t, v final minus v initial, t final minus t initial. These coordinates can be extracted from the graph. This is the initial point of 0 seconds, 0 meter per second, and the final point would be 8 seconds and 4 meters per second. Now we can apply the formula safely. Then v final is 4 minus v initial, which is 0, t final is 8, and t initial is 0, and that would be 4 over 8, which is 0.5 meter per second square, because meter per second, that would be meters per second square. Now exercise 1, the position of an object is given by the equation x is 3t squared plus 1.5t plus 4.5, where x is in meters and t is in seconds. What is the instantaneous acceleration of the object at t is 3 seconds? Now they're asking for the acceleration at a specific instant. However, the position is quadratic in time, which means that the acceleration is constant at all times, even if the question reflects that the acceleration is instantaneous, which means at specific instant. However, it is constant at all times. Now, how we're gonna extract the acceleration from this expression? We know that the position is given by x0 plus vx0t plus half axt squared. The quadratic term is unique and corresponds for the acceleration. By comparing both, we can say that half a is 3, which means that a would be 6 meters per second square. And the correct answer in this case would be B. Now a cart is moving in the positive x direction and passes the origin when time t is 0. The cart then moves with a decreasing speed. It stops. So initially it's moving in the positive x direction. It stops, then it's gonna move in the negative x direction with increasing speed. Which of the following graphs best represent the cart's position x as function of time? This is the easiest thing that we can do, because we know that if we're moving in the positive x direction, this means that v is positive, which means that the position will increase. Now it stops, then the velocity is 0 and the position will be momentarily unchanged. Then it's gonna move in the negative x direction, which means that the velocity is negative and the position will be decreasing. Then in this case, the correct answer would be A. Now the graph above shows velocity v versus time for an object in linear motion. Which of the following is a possible graph of position x versus time for this object? Now if we divide the graph into several portions, we notice that here the velocity is positive. At this specific point the velocity becomes 0, and here the velocity is negative. So initially the velocity is positive, which means that the position is increasing. The velocity becomes 0, the position will be unchanged, and here in this part the velocity is negative, which means that the position will decrease. And the best curve that describes this is A. A car is traveling down the highway at a speed v when the driver slams on the brakes and skids to a stop in a distance d. The initial speed is v, that would be v0, vx0, and skids to a stop, then the final velocity or speed is 0. It covered a distance d. Assuming the same frictional force, how far would the car slide if its speed was 2v? Then they have doubled the speed, which means at some point we're gonna use the factor of change. Now by how far, we need to determine the new distance if the speed or the initial speed was doubled. Now here, they didn't mention in the exercise itself that the acceleration is constant, but we're gonna consider this as an assumption. In this case, we can use the formula, which is v square x is equal to v square x0 plus 2a delta x, which is d, because we're not changing the direction. Now the final speed is 0, and we are interested in finding the value of d, then d would be given by minus vx0 square divided by 2a. Now we're going to apply the factor of change. Now the speed has doubled, so we replace it by 2. 2 didn't change, so we can replace it by 1, and we didn't change the acceleration, that would be 1, so the factor of change is -4. We're talking about the distance, so it's an absolute value, and the correct answer in this case would be E. Now, exercise 5, the data for the position x of a particle moving along a straight line is recorded at various times t. The position is plotted as function of t squared. The data points are shown in the graph. Which of the following shows an appropriate best fit line for the data? Remember that the best fit line is the line that passes among almost all the points or closest to these points. Now, A in this case would be the correct answer. If you look at B, so B, the best fit line doesn't lie among the points, as well as for C. Now, similarly for D, the shape of the best fit line doesn't fit with the plot of these points, as well as for E. Now, exercise 6, a car is moving along a straight horizontal road at a constant speed 80 meters per second. At the instant when the car passes a lay-by, a motorcyclist leaves the lay-by, starting from rest, and moves with constant acceleration 2 meters per second square in pursuit of the car. Given that the motorcyclist overtakes the car t seconds after leaving the lay-by, calculate the value of t, which is the time required for the motorcyclist to catch the car, and the speed of the motorcyclist at the instant of passing the car again. I suggest that you pause the video, try to solve it or understand the exercise, then refer back to the solution. Alright, let me explain what's happening exactly. Initially, we have a car which is moving at a constant speed given by 80 meters per second. At the lay-by, near the road, we have a motorcyclist. The instant the car reaches the lay-by, the motorcyclist is gonna accelerate and try to catch the car. Now, the best way to understand the exercise is to do a plot with an oriented axis. Now here we have the motorcyclist. The position of the motorcyclist is xm, and here we have the car. The position of the car would be xc. In the first part A, we need to determine or calculate the value of t, which represents the time taken by the motorcyclist to reach the car. So if you think about it, we need to calculate the time t, and t must be fitted in an equation. Then we need to solve this equation in order to get the value of t. But what equation we're talking about? This equation must be related to the physics of the problem. Notice that here they're telling us that the motorcyclist overtakes the car. So overtakes means that they will meet. And in this case, both bodies in motion will have the same position. So basically, if we have xm and xc explicitly in terms of time, then we can solve for t and we get the value. Then in order to do so, we need to refer the type of motion for the car and the motorcyclist. The type of motion of the car is uniform motion, and it's governed by this equation. Now, how about the initial position? Now, the origin of time will be taken when the car passes the motorcyclist at the lay-by. So initially the car was here. So let me say that this is t0. The car was here, as well as the motorcyclist. That would be the initial instant of time, which means the initial position of both the motorcyclist and the car, which will coincide with the origin. Then in this case, the initial position is 0, and the velocity of the car is given by 18. Then the position time equation for the car is given by 18t. What about the motorcyclist? It is accelerating, So this is the position time equation. The initial position is 0, and we know that the motorcyclist leaves the lay-by starting from rest, then the initial speed would be 0 and the acceleration is 2. Then the position time equation for the motorcyclist is given by t square. Now we can say that xm is equal to xc, the motorcyclist overtake the car, and we're gonna solve for t. Moving 18t to the other side, that would be t square minus 18t. We factor out t and we solve for t. We have two solutions, t1 is 0 and t2 is 18 seconds. And why we have two solutions? Because basically the motorcyclist and the car meet at two instants. The initial instant that we have chosen, which is at the origin itself, and the final instant, which is after 18 seconds after the motorcyclist have reached the car. And in this case, the duration is given by 18 seconds. Now in part B, they're asking us for the speed of the motorcyclist at the instant of passing the car. Now, after time has evolved, after 18 seconds, the speed of the motorcyclist would increase from 0 to some value. We need to calculate this value, and this can be governed by this equation. The initial speed is 0, the acceleration is 2, time is given by 18, and the final speed would be given by 36 meters per second. Now exercise 7, on a long straight road, a car accelerates uniformly from rest, reaching a speed of 45 meters per second in 20 seconds. It has to maintain that speed for 90 seconds behind the truck. The car then accelerates uniformly to 75 meters per second in a further 20 seconds. We need to calculate the total distance, the time taken, the average speed, and the average acceleration. So I suggest that you pause the video, try to solve it, then refer back to the solution. Okay. As you can see that here we have different phases for the problem, or different intervals. The first interval, when the car is moving at a uniform varied motion, initially from rest, a final speed by 45 meters per second, and this happens in 20 seconds. The second interval is uniform motion under a constant speed, which is given by 45 meters per second for a duration of 90 seconds. Notice that the exiting velocity of the first phase, or the first interval, would be the same for the second interval. Now for the third interval, again, the car would accelerate starting from 45 meters per second, reaching the final speed, which is 75 meters per second in 20 seconds. Now in order to calculate the total distance, we need to determine the distance covered in each phase or interval separately. Then in the first interval, if you look carefully at the given, we have the initial speed, the final speed, and the time. Then the displacement, which is basically the distance along a specific direction, would be calculated using this formula. And the distance would be 450 meters. For the second interval, the motion is uniform. Then we can use delta x is vxt, and the value of the displacement or the distance would be given by 40-50 meters. For the third interval, it is accelerating back again. So we can use the same equation as this. We have the initial and the final speed of this specific interval, and the distance would be given by 1200 meters. And the total distance for all the phases is given by 5,700 meters. Now what about the total time taken? So we simply add the time for each phase, and that would be 130 seconds. Now the average speed would be the distance over the time. We have the distance, we have the time, and that would be 43.85 meters per second. We know that the car along 3 intervals have been moving constantly or accelerating, but in average the speed is given by 43.85 meters per second, and the average velocity would be given by the final speed over the duration. The final speed, which is found in the third interval, is given by 75, and the initial speed in the first interval is given by 0. And in this case, the average acceleration would be given by 0.58 meters per second square. Exercise 8, car 1 and car 2 are separated by a distance of 1 kilometers. At the instant t is 0, car 1 is moving with a constant speed 20 meters per second toward car 2, while car 2 starts with an initial velocity of 10 meters per second, and its speed increases at the rate of 2 meters per second squared. The two cars are heading toward each other. We need to calculate the time taken for which the two cars meet, the distance traveled by car 1. So I suggest that you pause the video, try to solve and understand the problem, then refer back to the solution. Alright, so now we are partly more familiar with such type of exercises. We have two bodies in motion, car 1 and car 2. We need to represent the position time equation for each car separately. Since we in part A we are asked to calculate the time, then we need to fit the time in a certain equation, solve for this equation and get the value of time. They're asking for the time under which the two cars meet. Then in this case we can say that x1 would be equal to x2. Then a diagram in such type of problems would be helpful. This is car 1 designated by position as x1 and car 2 designated by position x2, but we need to understand initially what's happening or fix the initial conditions. At t is equal to 0, we will suppose that car 1 coincides with the origin and car 2 would be located somewhere here at a separation distance of 1000 meters. So let me repeat, at the initial instant car 1 would be at the origin and car 2 would be separated by a positive position given by 1000 meters. Then in order to write the position time equation for each car, we need to refer to the type of motion. For car 1, the motion is uniform, which is governed by this equation. The initial position is 0, the speed is fixed to be 20 meters per second, and the position time equation is given by 20t. Now what about car 2? First of all, they told us that the cars are heading toward each other, which means that the car 2 is moving in this direction. It's given an initial velocity of 10 meters per second. Here, what do they mean exactly of 10 meters per second? They mean the speed, or they didn't specify the direction, and this depends on your choice. Now, because it's heading toward car 1, which means that the velocity is gonna be minus 10 meters per second. Moreover, they told us it's speeding up, which means that the acceleration and the velocity must have the same direction, and the acceleration in this case is pointing toward the left with the value of, or algebraic value, minus 2 meters per second square. Now we are ready to set the position time equation for car 2, which is governed by uniform varied motion. The initial position is 1000 meters in the positive direction, the velocity is minus 10, and the acceleration is negative 2. And x2 would be 1000 minus 10t minus t squared. Now, at the meeting point, which is x1 is equal to x2, moving 20t to the left side, we're gonna have the following quadratic equation. Solving this quadratic equation on the calculator, we'll have two solutions, t1 and t2. t1 is the accepted answer because the time can never ever be negative, and you think about it, the cars will meet only in one point, because as they're heading toward each other, they will cross this point. Car 2 will keep moving in the negative direction while car 1 will be moving in the positive direction. Now in part B, they're asking to determine the distance traveled by car 1 when they meet, and in this case the distance, knowing the type of motion of car 1, the distance is equal to the displacement because it's an unchanging direction, which is given by v1 times t. The speed is uniform, which is 20, and it happens that they meet after 20 seconds, and the distance in this case would be 400 meters. Then thank you for watching, and see you soon in a new one.